In this class, we will be basically looking at the classless addressing. So in the previous class, we have seen the classful addressing. So in classful addressing, different points we have considered. So out of that, we have considered one point. There is one like what is the mask basically. So here into the mask, we have seen like the mask is the complete address. So out of that, so starting like for class A, this is the mask 255.0.0.0. Similarly, class B, class C. So for class A, leftmost 8 bits are ones. They will be providing you the the mask basically, the mask address. But in case of like if the last or we can consider like most significant 8 most significant bits are considered as the net ID into the class A type. Similarly, in class B, the leftmost 16 bits will be considered as the net ID. Similarly, in class C, the 32-bit leftmost bits will be considered as the net ID. The remaining bits, in case of like out of that, this will be the net ID. This will be the host ID. So this is the net ID in the class B, and this is the host ID. So in class C, this is the net ID, and this is the host ID. So host ID will be like total number of addresses possible for that particular class. So here in only 8 bits can be changing for host ID. So total 256 hosts are possible. So in case of class B, here to the power 16 hosts are possible. Similarly in class A, to the power 24 bits, that means to the power 24 means total power 24 addresses are possible or hosts are possible in this category. So because of the limitation to these categories, they are having only limited number of addresses for host available for you. So there is a limitation to addresses. So that's why there is a requirement of classless type of addressing. So here basically a particular IP address is basically constitute of network ID and host ID. So some portion will be indicating the network ID, some will be indicating the host ID. So in class A, 24 bits will be representing the host ID, 8 bit will be representing the network ID. Similarly in class C, last or most significant 24 bits will be the network ID and the least significant 8 bits will be the host ID. So how to find out the host ID and host ID and net ID? So net ID and network ID. So that is basically used IP address, whatever IP address is there, plus the mask. So with the help of IP address and mask address, we can find out what is the net ID and what is the host ID. So we will be looking at the next next PPTs. So that will be basically taking an example with respect to find out the host ID and net ID also, and the mask, how the mask can be used in coordination with the IP addresses to find out net ID and host IDs basically. So the basic idea of classless addressing is to accommodate more number of hosts. Okay, so there is a limitation in A, B and C, so we can remove it. Okay, so here the class full addressing, which is almost obsolete and is replaced by classless addressing, because if we do the class full addressing, there is very much of wastage of addresses, but there are more and more number of users are there onto the internet, so there is a requirement of large number of addresses. So that's why the class full addressing is obsolete now, that it is basically used by the classless addressing. So here, to overcome the address depletion and to give more organizations access to the internet, the classless addressing was designed and implemented. So in this scheme, there are no classes, but the addresses are still granted in blocks. So addresses will be granted in blocks and no class is there. So next is like to simplify the handling of addresses, the internet authorities impose 3 restrictions. So 3 restrictions on the classless address blocks. So if there is a classless addressing is going to be there, so these 3 points needs to be there. So the addresses in a block must be contiguous. That means they should be allotted one after another. So continuous should be there in nature. And the number of addresses in a block must be in power of 2. So power of 2, so 2 to the power 0 means 1, 2 to the power 1 is 2, 2 to the power 2 is 4. Likewise, always the number of addresses given to a particular organization or group should be in the power of 2. The first address must be evenly divisible by the number of addresses. So whatever the number of addresses are there, that means 2 to the power something, number of addresses. So whatever the first IP address or first address would be there, that should be divisible by the number of addresses. So these are the three conditions should be satisfied in classless addressing. And these are the points that can be asked into the numerical type of questions. So, and we will be dealing with the numericals questions, some of the numerical question in that number of subnet, number of subnet address, broadcast address, number of hosts per subnet, how we need to find out what the first host ID, what is the last host ID, we can find out that will be considering. So this is the formula given. So yeah, we will be taking an example. So in that here it is saying like 19.3 figure, there is a block of addresses given. So this is the block of addresses given. Okay, so here it is given the first address is this, the last address is this, and it is given in decimal and binary likewise. Okay, so this is given. So total addresses are 16. So total addresses are 16. So how it is basically given. So here it is seen like we need to check whether it is classless addressing or not. So to find out that, so we can see that the restrictions are applied to this block. So how it is given? So addresses are contiguous. So contiguous in the sense, so it is addresses, first address 32, second one is 33, likewise 34, 35 up to, if we add 16 to 8, okay, so it will be coming out to be like 47. So complete addresses are 47 up to 47. So 32 to 47, if we consider it, it will be coming out to be like 16 addresses. Okay. And also the first address, and also like total 16 addresses are there. So 16 is to the power 4. So it is that total number of addresses are into the power. That is the second condition. First condition is addresses are contiguous. The first is satisfied. The second is also satisfied. The third one, the first address when converted to a decimal number, so it is coming out to be this number, and when it is divided by 16, it is coming out to be an integer. That means it is completely divisible. So all three conditions are satisfied. That means it is a classless addressing. So this was the classless addressing. So here one point we can note it down like in IPv4 addressing, a block of address can be defined as x.y.z.t/n, where x.y.z.t defines one of the addresses. So out of the complete host addresses, like if a network is there, in that different hosts will be there. So one host address will be given. This will be x.y.z.t /n defines the mask. What is the number of bits into the mask? Okay, so that is there. So here the first address in the block can be found by setting the rightmost bit, 32 minus n bits to 0. So first address, how the first address is defined? So that will be by setting the rightmost 32 minus n bits to 0. So that will be the first address. Similarly, there is an example with respect to that. So suppose there is the IP address is given /28. So /28 means 28 bits are there into the mask. So 28 bits are there into the mask. So the remaining 32 minus 28 is 4 bits. So that means if left rightmost 4 bits are made to 0, that will be the first address. So that what we will be doing is we will be converting this to binary. So after converting to binary, so rightmost 4 bits will be made to 0. So this is the rightmost 4 bit. So this is the address of the first host basically. And once it is converted to decimal, this is the address. So this is how it will be there. So how to find out the first address? So with respect to IP address and its mask, this is the mask bits. So we can find out the first address and also we can find out the last address. How we can find out the last address? So the last address in the block can be found by setting the rightmost, means 32 minus n bits to 1. So that will be giving out the last address. So the same example, this was the address given. So last four digits. So last four digits are this will be made to 1. So last four digits are 1. So now it is converted to a decimal equivalent. So in decimal equivalent, this will be there. So this will be the last address. The next point is the number of addresses. So what is the total number of addresses possible into a given network or into a given block of hosts? So in that, so once an IP address is given and the number of mask bits are given, so that can be used like 2 to the power 32 minus n. That will be providing the total number of addresses possible. So in this example, it is like 28 is the n value. So 2 to the power 32 minus 28 is equals to 2 to the power 4. So 2 to the power 4 is equals to 16. So this is the total number of 16 addresses are possible. So yeah, the same thing can be done with one another method. Okay, so here same previous example, we can find out the first address, last address, and the number of addresses by using one other method. So another method is like, suppose here we only have suppose 28 means slash 28 is given, means there are 28 mask bits. If 28 mask bits are there, that means 28 mask bits are given, means leftmost 28 bits will be there, that will be for the mask. So this is the mask basically. So mask address will be this. So with respect to the mask address, we can find out the first, last, and number of address. Along with this mask, we should be having one plus, we should be having any one IP address. So in the previous question, the one of the IP address is given. So IP address that is given was this one. So this was the IP address given. Okay, so we need to use the same. So one IP address plus mask is required to find out the first, last, and number of addresses. So first address, how we can find out the first address? So first address can be find out by ANDing the given address, given IP address basically, with the mask. So here the given IP address is this, and the mask was 28 bits. So leftmost 28 bits as 1 and 4, remaining so 4 is 0. We will be doing the ANDing. So after doing the ANDing, this will be obtained. So this will be the first address. Similarly, to find out the last address, what we need to do is we need to take the same IP address that is given into the question, and then we need to complement the mask. It is mask complement is equals to mask complement. So after taking the ones complement it just converting zeros to 1 and ones to 0. Then we will be taking here the ORing. We will be doing the ORing here. After doing the ORing, whatever is the value, that is the last address of that block basically. Next, we need to find out the number of addresses. So the number of addresses can be found by complementing the mask. Okay, so after complementing the mask, we need to find out its decimal equivalent. Because it is in binary, we need to find out its decimal equivalent. So in decimal it is 15. So whatever is the value, we need to add 1 to it. That will be 16 will be the total number of addresses. This is how we can find out the total number of addresses. Or this is another method to find out the last, first, and the total number of addresses. The same thing can be given here now. It was given previously, and here this was given. So suppose this first of all, here the first address is considered as, because these are like one network is there. Inside one network there are different, means 16 hosts are there. So out of 16 host IDs, the first host ID is considered as the network ID. If this is the network, so there will be an ID address. So the first address always is considered as the network address. So here 205.16.37.32 will be the network ID /28. So this is the network ID, and remaining 15 will be the hosts available into that. So that will be the total 16 addresses. So 16 addresses. Out of that, the first address will be indicating the network ID. Okay, so this is given here. A network configuration for the block this is likewise. So yeah, the same point is given here. Like the first address in a block is normally not assigned to any device. It is not assigned to any device. It is used as the network address that represents the organization to the rest of the world. So like in any condition, like in our university also, so a complete like university is uh, should be having a network ID, and other hosts IDs will be for other users, but there will be a first address that will be for the network, this complete network. Okay. So here the frame in the character oriented protocol. So here it is a character oriented protocol. Then in that we have already seen like, so out of 32 bits total, 32 bits are there. So out of that 32 bit IPv4. Okay. So 32 bits are there. So 28 bits will be considered as the network ID or the network prefix, and the 4 bits are like the host ID. So it is not like always the network ID will be 28 bit. So in our previous example it was given 28, so that's why this 28 is written. So that means some portion of the 32 bit, so 32 bit, some portion will be the net ID, network ID, and some portion will be the host ID. So host ID will be decided based on the number of addresses required or number of hosts required. If suppose hosts are required is 256, in that case the host ID will be represented by 8 bits. Okay, so here this will be the 8 bit, and the remaining 24 bits will be for the net ID. So total overall 32 bits will be there. So here each address in the block can be considered as the 2-level address, can be considered as the 2-level address. So 2-level address means here the same is 2-level address. Okay, so 2-level hierarchical structure. The leftmost n bits prefix is defined the network, and the rightmost 32 minus n bits defines the host. The same thing is given in 2 words. Yeah, even here configuration and addresses in a subnetted network is given. So it's like this dotted box represents a complete network. So dotted represents a complete network, and it is given 17.12.14.0/26. That means this is the first address. First address means this is the network address. First address /26. 26 means 26 leftmost ones are going to be the mask, then remaining 6 bits are going to be the, yeah. So here the complete 32 bit, out of 32 bit the 26 bits is for the net ID, that means network ID, and the remaining 6, because total 32 bits will be there, 6 will be the host ID. So if 26 here 6 is there for the host ID, that means total possible number of hosts can be there 2 to the power 6. So 2 to the power 6 means 64. 64 hosts are possible if this is the case. So here is the case. Okay, so out of this 26 is there here network ID, and 6 is there. So out of that 6 bits are there. So if we consider 1 2 3 4 5 6 bits are there. Okay, so here this complete network is divided into sub network. So sub network 1, sub network 2, sub network 3. So if this is the sub network, that means there will be some network address, network address. So for sub network also there will be some address. So there is a smaller network out of the complete larger network. So there will be an address. So it is 17.12.14.0. So the same thing is given here. Okay, and it is given like 27. It is given 27. That means here in the sub network 1, the 27 bits are going to be considering the network address, and the remaining the remaining 5 bits are going to have the host ID. That means 5 bits are going to have the host ID, means 2 to the power 5. That means 32 hosts are possible. So you can just see the address. So address is, the first one is 1, because 0 will be for this subnetwork address. So for this subnetwork address, the address will be 01. Okay, and here the 1 will be the first host, the second, third, fourth, likewise that should be 32. So up to 31 it will be going, because the first one is the network subnetwork 1 address. So total 32 hosts are here possible. Similarly, in this case, it is given like subnet 2 and 3 is given. So in that case, the address is considered to be like here. The addresses are like here 17.1, 0.14.32 is given. So 32 is given here, slash 28 is given. So 28 is given means out of 32, 28 is for the network ID. Okay, so we can consider. Okay, so out of that, the remaining 4 will be the for the host ID. So 4 is host ID, means 2 to the power 4 means 16 host IDs will be there. So 16 host IDs we can just consider from 32 to 47. The basically it will be 32 to 47. So 32 to 47. So that will be total 16. So first one will be for the network, subnetwork 2, and the remaining 15 will be for the host. Similarly, this one's there. So this is how basically it is considered for different categories. Okay. So this is how the configurations is done of addresses for different subnetwork address also. So you can just go through it to have a clear picture. Yeah, so this configuration, if there is a subnetting is being used, in that case it will be considered as a 3-level hierarchy. So 3-level hierarchy means if subnetwork 1 is there, so 26 bit will be for the network ID. Then this, if we take 27 bits, 26 plus 1, it will be the subnet prefix basically. And this 5 bits will be the host address. Similarly for subnet 2 and 3, 26 plus 2, 26 will be the network address, and the 26 plus 2, that is 28, will be the subnet prefix, because in subnet 2 and 3, 20/28 was used. Here /27 was used. So 27 will be subnet prefix, and remaining 4 will be the for host. Okay. So here an example is given. So here an ISP is granted a block of addresses starting with this address /16 is given. /16 in the sense, out of 32, 16 is used for the mask and the remaining 16 is used for the host. So that means 2 to the power 16 will be 65,536. So this is the total number of hosts possible. Okay. So here it is given like this is the starting address of the ISP. Okay, that means this is the network address of the ISP. /16 means 16 bit is used for the mask and remaining 16 bit for the host. So here the ISP needs to distribute these addresses to 3 groups of customers as follows. So first group is having 64 customers with each needs 256 addresses. Second group has 128 customers, each needs 128 addresses. Third group is having 128 customers, each needs 64 addresses. So design this sub block and find out how many addresses are still available after these allocations. So we need to find out, after allocating the addresses to these customers, what is the remaining addresses out of 65,536 addresses. Okay, so how we will be starting? The first we will be starting with here. So for the first group, there are 64 customers and 256 is needed. So 256 addresses are needed for the 64 customers. So what one customer will be having? So here 64 customers are there and each needs 256. So if each needs 256, that means total number of bits for 256 hosts will be like log 256 to the base 2. That will be coming out to be 8. That means out of 32 bits, 8 bits will be used for the host. Okay, so remaining 24 bits will be used as a mask. Okay, so the first address that will be there is starting with 190, then dot 100.0.0 slash, it will be 24 because 24 is coming out to be the mask. Then this will be the first customer, first address 0, then last address will be the 8 bits will be changing starting with 0000 to maximum 111, total 256 255. So 0 to 255, total 256 addresses are there for the customer 1. The next customer will be having the 190.100 dot, instead of 0 it is 1 now, the 0 then 1, then dot 0 starting with, then it's going to 255. So likewise the last customer 64th customer will be starting with 0, this will be 63.0 to this. So total 64 customers, each is having 256 addresses. So total 64 into 256, this is the total address utilized by the first group basically. In the second group 128 customers are there and each needs 128 address. So 128 address means log 128 to the base 2, that is come up to be 7 bits. So 7 bits will be like host bits. So host will be there. So remaining 32 minus 7, that is 25 bits will be for the mask one. So okay. So out of that, so 25. So 25. So what is the first address? So first address, how we need to find out? So one of the IP address we can find out the first address, and it will be just because it should be in continuous because it is classless type of addressing is there. So this is the last address that is allocated. So 190.100.63.256. The next address will be 190.100. Because this is, we can't increase it further, so it will be coming out to be 0 next. And then once it is going to be 0, it will be increased with 1. So it is going to be increased with 1. So it is 64.0. So that slash, then whatever is the next net ID in the next case, net ID, the mask is basically 25, so it will be 25. So 190.100.64.0 slash 25. And it needs 128 addresses for one customer. So first customer will be having starting address this. The next it will be going, instead of 0 to 255, now it will be going to up to 127. So 0 to 127, 128 addresses in this case. The second customer will be in continuation to this. So up to here 127, next address will be 64.128, then next will be 255. So it is 128 address. So that means total that it can have is likewise. So 128 customer. So once it will be increased, so it will be 127, and this will be the last address in case of second group. So 128 customers, each needs 128 address. So total this much of address is utilized in the second group. Next is the third group. So here is like 128 customers are there, and each needs 64 addresses. Okay, so 64 addresses means log 64 to the base 2, that means coming out to be the 6. So 6 bits will be used for 64 addresses. So we'll be changing last 6 bits. So this was the last address. After that, the next address will be like 190.100.128, one more than that, 128.0. So this 128.0, this will be the first address. Then we will need to change the 6 digits. So we need to change the 6 digits. So once we will be changing, it will be 0. Then 6 digits we will be changing, it will be coming out to be 63 for 64 addresses. Next will be 128.63, next is 64. Then it will be 64 addresses. And finally 128th customer, this will be the address. So total 128 cross 64. So this is the total address. So total possible address was 65,536, and the total allocated in these 3 cases is 8192, 16,384, 16,384. Total that will be 40,960. So out of this will be subtracted. So after subtracting, this is the address available still. So its allocation is given here. So for the ISP, address range was 190.100.0.0. So this 16 bits were changing. So 16 bits starting 0, 16 bits maximum 1, so 255 to 255. So out of that, in this range only we have to allocate. So this was the group 1, group 2, group 3, and these are the available addresses. So this is how the address allocation can be done by the ISPs. Next point we will see is the IP addressing version 6. So this is basically required because of the limitation of IPv4. That limitation, one of the uh, limitations of IPv4 is the address depletion. So despite all sort of solutions that we have done, like the classless, even if we have done the classless addressing, then also it have the short term solution of classless addressing, then also it could not be able to overcome the requirement of the addresses, or the hosts are increasing, so there is a requirement of large addresses, but there is an address depletion is still a long term problem for the internet. This and other problems in the IP protocol itself have been the motivation for IPv6. So here IPv6 will be having 128-bit long. It will be using 128-bit instead of 32-bit in IPv4. So here the IPv6 addressing how it is represented. It can be represented in binary or hexadecimal colon notation. So in binary means total 128 bits we have represented in terms of zeros and ones. So that is the binary. Next one is hexadecimal colon notation. So it is converted into 128 bits are there, so 16 byte. It can be converted like to 32 hexadecimal digits. So 32 hexadecimal digits. So this is represented in terms of colon. So hexadecimal digits, four group of 4 hexadecimal numbers with a colon. 4 hexadecimal number with a colon. So this is how it basically represented. So that's why it is called like hexadecimal colon notation. So to make addresses more readable, IPv6 specifies hexadecimal colon notation. So in this notation, 128 bits is divided into 8 sections. So this is a section. Each 2 byte length. So this is of 2 byte. 2 byte in hexadecimal notation requires 4 hexadecimal digits. So 2 byte means 16 digits. So 16 digit can have 4 hexadecimal digits. So this is 4 hexadecimal digits. So therefore, address consists of 32 hexadecimal digits with every 4 digits separated by colon. So this is the representation of IPv6 addressing. Next one is abbreviated, because still the 32-bit hexadecimal number is very large. So there is a requirement of abbreviation. So although the IP addresses even in hexadecimal format is very long, so many of the digits are zeros. So in this case we can abbreviate the address. So if there is a zeros into the addresses, we can abbreviate it. How we can do it? So here the leading zeros of a section can be omitted. So inside a section, this is a one section, section likewise. So the sections having leading zeros can be omitted. Only leading zeros can be dropped, not the trailing zeros. So that means this was the original representation. After abbreviation, it is done like this is represented same because there is no zeros. Here this is the leading zero. If leading zero is there, that will be omitted. Only 74 will be written. So here if 0 is there, complete 0 is there, one section is complete 0, so it will be represented by 0. Complete is 0, 0. Complete 0, 0. In between and the hexadecimal number there is a 0, so it will be keep it as it is. Here complete 0 is there, so it will be represented by single 0. Here FFF, then this is trailing 0. So trailing 0 will be put as it is. It will not be omitted. This is the first stage of abbreviation. Next is further it is more abbreviated, like whenever there is like more than one section is having continuous zeros, then it will be combined, it will be omitted, and it will be represented by two columns, basically continuous columns without any number. So okay, so this is how it will be represented in terms of abbreviations, and that abbreviations will be with respect to the number of zeros that are available. So here an example is given. So here we need to expand the address that is given here to its original form. So in that case, this is basically representing each section. Okay. So it is basically going to have each section. So each section should be having 4 hexadecimal numbers. So first of all, one IPv6 is having total 8 sections. So we need to convert it into 8 sections. So the first section is this one, second section, then this will be like the third section, this is fourth section, fifth section. So 5 sections are there. So 1, 2, 3, 4, 5 sections are there. So remaining 3 sections are there. Okay, so we need to divide it further, 3 sections. So 1, 2 and 3 sections. So these 3 sections are there. So what we need to put it, we can do that. Okay, so here, so one section is 0, so 4 zeros should be there because 4 hexadecimal numbers should be there. If it is 15, only 2 hexadecimal numbers are there, so the 0 will be padded likewise because 4 hexadecimal numbers should be there. Similarly, here 4 is there, 4 is there. Here 2 is there, so 2 extra will be added. 1 is there, 3 extra is needed. Similarly, so 1, 2, 3, 4, 5. 5 sections are completed. Now next 3 sections will be all zeros. So this will be the original value. Yeah, one more point to IPv6 is basically the type prefixes. So in IPv6 addressing, basically some portion of the 128 bit is basically fixed for providing a category. So here IPv6 has a much larger address space, that is 2 to the power 128 addresses available. A few leftmost bits called the type prefix in each address defines its category. Okay, so it will be defining a category, type prefix. The type prefix is a variable in length, but it is designed such that no code is identical to the first part of any other code. So it is having the type prefix that basically specifies, like if it is starting like leftmost 8 bits is 000, it will be considered as a 0 type of address. So these are the different type prefixes are available for IPv6 addressing. Okay.